You ready? Okay, let's get started. You have to see me 2 more times, or today and then 1 more time. And then maybe we see each other again in other classes. That would be nice. But today, if everything goes well, is our last lecture. And I want to do 2 things. I want to finish this topic of order and forward dynamics, sort of this audacious claim to say I can do forward dynamics with linear complexity, which up to now we have learned requires the inversion of a mass matrix, which by itself is an order n cube operation. And here we say we can do without. And it's a bit of a complex topic, but I like it because it reiterates the usefulness of the things that we've done here. That's going to be the first half. The second half, I want to do a bit of a summary, what we learned. I want to talk about what's next. I want to talk about the exam. But let's start with this. And so far, this is all based on a claim. And the claim that I made is that if I grab an articulated system, so not just one single rigid body, but something where there's more bodies attached to it. But I grab one of these bodies, which we call the handle, and I apply an acceleration to the handle. The force that I need to create this acceleration is something that is linear in the accelerations, plus some bias term, where importantly these bias terms do not depend on accelerations. The bias terms depends on position, velocities. We kind of know that because if stuff is moving in this articulated thing, if something is moving, we get bias accelerations, we get inertial forces, which we will feel here, right? So that should make sense. If there's a motor, if that creates some torque, we should feel a reaction here. If there are external forces, we should feel a reaction here. But the important notion is that none of this is acceleration dependent. Yeah? The accelerations come in only linearly. And the way you should read these bias forces is if I set the accelerations to 0, my forces that I apply just to keep the handle here, the blue body, stationary, those are the bias forces. That was my claim. Kind of a bold claim, but if we build this up slowly, maybe you believe me. And I started by saying single rigid body clearly fulfills this rule. The only thing that we've done here is we've rewritten the Newton-Euler equations of rigid body motion in a matrix form using these spatial quantities where we combine accelerations, linear and rotational, into a single vector, and the same with forces and torque. So this checks out for a single rigid body. And you kind of can now see where this is going. If I can say this checks out for a single rigid body, and I can show you that if I combine 2 single rigid bodies, I get sort of the same equation. So combine 2 rigid bodies, pick one of them as a handle, I get the same equations. I can then add more and more bodies as we go along and slowly build up the articulated inertia for a very complex system. And this is where we basically ended. The way to understand this, it's easier to think about it the reverse way. If I say, if I have an articulated inertia or an articulated body that I cut apart, which is nothing else than saying I do a free body diagram, and all I do is I replace that joint here with a 6-dimensional force torque quantity that has some active components and some passive components. But it's basically a 6-dimensional quantity. And then I consider each of the subsystems that I get as an articulated inertia with their own handle. System 1 has the handle of the original undivided system. System 2 has a new handle that we call C here, which is going to be sort of the new handle for our second system. And we can, in a sense, write the same equations that we stated on our previous page, this equation, with the only difference that the forces in green right, acting here on the large system are different here because they're a combination of the external active forces and the constrained forces on body B, and they're only the constrained forces on body C, right? So it's just shifting our perspective where at some point we say we grab this body and shake it and we basically feel the articulated inertia. And in this case, the constraint, the joint grabs the body, grabs the handle, shakes it, and feels the articulated inertia. And going backwards, right, in the sense of assembling things, we would know that we can write the equations of the articulated inertia of these two bodies in the following form. We can state that. You may not believe me yet that I can do this for articulated bodies, but you should believe me at this point if these are two individual bodies, independent, rigid bodies, I could write their equations of motion in this form, right? It's just a restatement of the Newton-Euler equations of rigid body motion. And the question is, can I state basically this equation for the system on the left, which in other words is asking ourselves the question of what is FB hat B? What is this force that I need to apply to generate this acceleration? Where I kind of see that acceleration ABA as something given, and I'm trying to compute this, this force here. And you can see if the resulting equation that gives me FBB as a function of this, if it has this form, we can now, through recursion, deduct that this form holds for all articulated bodies. Well, not so fast. Because the way to do this would be to take these two equations and eliminate the unknown quantities. One unknown quantity in this context is the constrained force that we should eliminate. Unfortunately, there's a second unknown quantity. That's the acceleration of this handle C, of the green handle. We don't know either of these quantities. They're six-dimensional quantities, so we have a total of 12 unknowns. And I can only, manipulate basically or solve 6 equations to get one of the unknowns and then insert it into the second equation. So if I could solve this here for blue, insert it here, I would still have my acceleration as the unknown. So that doesn't work right away because we don't know what the constrained forces are. We don't know what the accelerations are. However, between these two handles, between blue and green, there's a joint. And that joint gives us a bit more information between the constrained forces and the relative acceleration of these two handles. And I want to write, they haven't proven this yet, so I will show this on the next page. It's a bit involved, the math, but maybe you believe me just from experience of what we've seen so far, that I can say the acceleration of the green handle is somehow dependent, let's write this as BC transposed hat, is somehow dependent on the acceleration of the blue handle, body B, right? If body B moves and these two bodies are connected, body C has to move as well. Plus, there is some motion that is generated which comes from the joint. And I will just state that this motion is somehow generated through a joint Jacobian, right? So the Q double dot, if this is a rotational joint, right, the rotational acceleration is somehow influenced the acceleration of body C. And there's going to be some bias accelerations, translational and rotational, so that's why I write everything here with the hat. And those bias accelerations, they only depend on positions and velocities. I will prove this in a second, but it somehow reduces our problem size. Before I said we don't know the acceleration across the joint. which is a 6-dimensional quantity. But that's not true. The only thing that we don't know is the acceleration of the joint variables. Everything else is a constraint. There's no motion. So if I have a purely rotational joint, I don't know the acceleration across that joint, the q double dot of that particular joint, but I know that this rotational joint is not going to allow translational motion. I know that this rotational joint, right, single rotation axis, is going to block rotations about the other two rotation axes. So there's a lot of information in here which basically reduces these 6 unknowns to just one. If I have a single motion primitive, ball and socket joint, this would be a 3-dimensional quantity, depending on what type of joint you have, right? We will reduce this to fewer dimensions. If I now think about the constraint force here, we have a very similar equation, or we've seen similar equations in the past, where I say I want to project my constraint forces into my joint space, which is going to use the same Jacobian that I postulate exists here, now with a transpose, and that is being multiplied with my constraint forces that occur within this joint. We've seen this when we talked about the recursive Newton-Euler algorithm. We've seen this in other instances where we basically do a Jacobi transpose mapping, where all I will do is essentially a power equality over these quantities here. About torque times q double dot. The power produced in this joint will have to be this force times the associated velocity. I didn't write down the velocity equation, but this is what we had on the previous page. That gives me also some information, because if I look at this, I cannot freely select the 6-dimensional quantities of this combined constraint force, joint and constraint force, because I have a motor in here, right? And for that motor, I know exactly what the torque is going to be. Resolving a forward dynamic problem, tau is given, q double dot is not given. And there's a certain duality in these quantities, right? From the actual true constraint forces, I don't know the forces, but I know there's no motion. And for the active motion primitives, I know the force, or the generalized torques, and I don't know the acceleration. So overall, what this will give me here is an additional 6 equations, or it will reduce the number of unknowns by 6, where I started by saying there's 6 I don't know here and 6 I don't know here, where the reality is I have nq quantities that I don't know here, or I should say n because it's just the number of motion primitives in this joint, n quantities that I don't know here, but I have n bits of information about the joint forces. So just as a counting argument, this should check out. Let's see where this goes. And I want to start with a little bit of math that I will rush over, and all I want to show you is that this expression here holds, that I can write the acceleration across a joint in this form. To do this, I pull the information from chapter 4, where we already had a closed form expression for the rotational acceleration of my successor body, which depends on a bunch of stuff, right? The acceleration of the predecessor body, the angular acceleration across the joint, and some bias acceleration that basically came from the fact that my joint may be moving with constant rotational velocity, and the predecessor is moving as well, which means that rotation axis is shifted around, which results in an angular acceleration. And I can expand this and rearrange it, and I basically get here for my acceleration of the successor body, it is something times the acceleration of the predecessor body. We just identify this as a rotation matrix. It is something that I can write as a Jacobian times a joint acceleration, where this acceleration here, right, this omega dot, we wrote this as r times q double dot. We had this expression where we said this is some Jacobian r times q double dot, and then I just redefine sort of a s ds times ap ds transpose times r as this orange Jacobian here. The main point is that part is linear in our joint accelerations. And then I have stuff back here, which I marked in green, which only depends on velocities. So that is a pure bias acceleration. And for rotational velocities, you see sort of this nice format that I have laid out here. Acceleration of some successor depends on the acceleration of a predecessor times some Jacobian q double dot plus some bias accelerations. For translational motion, this gets much more involved, so please don't try to follow this in detail. I provided here in case you ever want a record of this, but we basically had these 3 steps where we go from predecessor to predecessor joint coordinate system, predecessor joint coordinate system to successor joint coordinate system, successor joint coordinate system to successor center of mass. These 2 steps are almost the same, apart from the sign, which comes from the fact that we go from, in our description of the joint, from successor to successor joint coordinate system. But as we move through the kinematics, we go in the opposite direction. And this expression has these extra terms which account for the acceleration across the joint and some bias terms across the joint and so on. If I plug each of these into each other, expand and sort a little bit, I get this nightmare of expressions, which fall in different categories. Blue, stuff that depends on the predecessor acceleration, no problem. Green, stuff that only depends on velocities, no problem, right? We just sum that up and say, let's call this a bias accelerations. In forward dynamics, I can always compute it because I know what my velocities are. So each of these quantities can be computed. Orange is stuff that depends directly on the joint. So this r double dot, RdPdS double dot, I can write as a Jacobian. We call that S, a joint Jacobian for translational motion, S times Q double dot. So that is linear in Q double dot. The stuff in purple is a little bit more annoying because it contains angular accelerations. And those, we have to have a second look at this. So this is what I do on the next page. This little star here means we're looking at the 3 terms that are marked in purple. So if you read this at home, that you oriented and simply copied these 3 terms. And now I have to basically reason about what of this stuff depends on the motion of the predecessor. And an important realization here is that predecessor body and predecessor joint coordinate system move with the same rotational rate. So it doesn't matter whether I write dp or p. And the same holds for the successor. It doesn't matter whether I wrote ds or s. So I can express all of this either as a rotational or as a function of angular velocity of the predecessor body, or of an angular velocity of the successor body, or angular acceleration. And for the angular acceleration of the successor body, we have already developed this expression here, right? We said that depends on the angular acceleration of the predecessor body plus this Jacobian plus some bias terms. And then I just expand and rearrange and do the trick where I flip the cross products and get stuff to the end. And at the very end of this, I end up with something that has this form, where I have stuff that only depends on my acceleration, angular acceleration of the predecessor. I have stuff that depends on the angular acceleration of the joint, here expressed by this rotational Jacobian times Q double dot. So this is where all the omega s dot ended up by making the substitution here. And then I have stuff that I would classify as bias terms. And I then can basically take this expression, the simplified expression, and put it back into here, where I simplified this as ASP times that, and then everything that I marked in green I put together into one expression, and I shouldn't forget about this. So we get stuff in green, which are the terms from the previous page, plus the new bias term, all a bias acceleration, translational bias acceleration. Then I have sort of the translational motion of the joint, which is this Jacobian times q double dot. I have the rotational acceleration across the joint, which is this Jacobian times that plus some lever arm. So this shows up here. And all together, you can kind of see how this gives me a overall joint Jacobian. And then this is stuff that depends on the acceleration of the predecessor, right? Linear acceleration is simple. If the predecessor moves with a certain acceleration, the successor should have the same acceleration, just in a different coordinate system. But if the predecessor is undergoing an angular acceleration, then stuff requires some cross products and lever arms that we see here. And then I can take this expression for translational acceleration, that expression for rotational acceleration, and press it all into a matrix form that I can write this as spatial quantities, where the bottom row is the angular acceleration and the top row is the linear acceleration. And we can kind of nicely see that this follows a certain pattern, that here we actually see these transformation matrices that I introduced in the last lecture. And then here we see sort of a nice structure for our Jacobian. A lot of math, not a lot to learn here, other than that you believe me now that this here is true. Right? I can do this. This is just an abbreviated form of writing my kinematics across a joint, and it reduces the 6-dimensional unknown to the n-dimensional unknown of how many joint motion primitives we have in this joint. Good. Any quick questions? Focus here on concepts. And now we are looking at 4 equations. The relationship acceleration across the joint that we just looked at, the projection of the contact forces, of the constraint forces into the joint, and then these 2 equations of the subsystems, right? Where I say the acceleration of handle B times mass of the subsystem or articulated inertia of the subsystem is given by these forces, and the acceleration of handle C times the articulated inertia of the second subsystem is given by these quantities. And what now follows is just plug and evaluate. And where I start is with this, right? I can compute tau if I know Fc. So that's my starting equation here. Where do I get Fc from? Well, from this equation, right? I can solve my second equation to say my constraint forces are ma2 times AC spatial minus this bias force. This is what I get here. And then AC spatial, I get that from here, right? And I plug that in. So for this quantity, I plug in this entire equation here. So this is what we have in the parentheses here. And then I start sorting. I look at the stuff with my unknown. And the only unknown I have left in this equation is q double dot. Everything else is now known, right? My Jacobians are only position dependent. I assumed that I know my articulated inertia. These are position dependents. I assume that I know the acceleration of body B, right? That's the question that I want to answer in the end. If I have a certain acceleration for body B, what is the green force that I need, right? So this I can treat as known. Jacobi, bias forces, bias acceleration, bias forces are all given. That's the only unknown, right? So let's pull this out. So we get this Jacobian times that mass times that Jacobian times q double dot equals all the rest, which is tau. And then the terms from back here, acceleration of the predecessor, bias acceleration, bias forces, all of that stuff moved to the other side and then projected into this particular joint using this Jacobi transposed mapping. And now I have an expression that I can solve for Q double dot. And this is where I want to stop, because even though a lot of this, what we did, was very involved, this is something that we've seen many, many times before. Right? What I'm saying here is I have an acceleration, right? And it's not the entire Q. This is not generalized coordinate space. It's Qi. It's the space of the motion primitives of this particular joint. This is something between 1 and 6 dimensions. Times some mass matrix equals the corresponding force quantities, which of course means that the motor torques, which live in that same space of n motion primitives, and bias stuff that just depends on velocities. In this case also depends on accelerations of the predecessor. So I have this projection. Again, I did some projection where I moved from one coordinate system, generalized coordinates, into a new coordinate system, just at one joint, right, with its 1 to 6 motion primitives. And we see the same form here, right? Some Jacobian times mass matrix times Jacobi transpose. This is how we computed mass matrix for the original system, right, where we went from some other space, Cartesian space, into our generalized coordinate space. Now we go from the generalized coordinate space to our joint space. And we do exactly the same thing, right? We project it again. Same idea. We've seen this when we talked about collisions, right? Our space was here we had our contact space mass matrix, right? Now this is the inertia that the joint sees, right? That's a physical quantity. If this is a pure rotational joint, this is a scalar quantity that has units of kilogram meter squared, right? It's an inertia. And you can immediately see there's a linear relationship with, what torque do I apply, what accelerations do I get. Projected into yet another space. Same thing now, 4th time. Much more complicated than what we saw when we talked about collisions, but that's only because we have to carry all these bias quantities with us, right? When we talked about collision, all this here was inherently set to 0, and we ended up with something that says m lambda times c double dot equals, or in this case, delta c dot, I should say, jump in velocity equals capital lambda, right? And now, because we're looking at continuous dynamics, of course, I cannot ignore all these bias terms. I have to carry them around with me. But that's the core idea, right? To take the equations of motion and project them into a single joint. And now I can solve them. What's the computational complexity of solving this equation of motion? Right, so solving for Q double dot. That's what we want. We want to do forward dynamics, so I want to know Q double dot. How much time does it take to compute this quantity? And how does that time scale? I think that's the more important question, right? This is pretty involved back here, but how does it scale with the number of degrees of freedom in our entire system? Well, what do you have to do to get Q double dot? Q double dot I, right, the accelerations of this particular joint. What do you have to do? You have to invert this mass matrix here. What's the dimension of this mass matrix? Well, it depends on the dimension of this guy, right? And what are the dimensions of this guy? 1 to 6. Somewhere between 1 and 6. Right? So the worst you can have here is a 6 by 6 matrix that you have to invert. There's no NQ here. Right? The total number of degrees of freedom in the total system, it doesn't matter. This is, in the worst case, a 6 by 6 quantity. this is a 6 by 6 quantity. This is a 6 by 6 quantity. This is a 6 vector. This is a 6 vector. This is a 6 vector. This is, in the worst case, a 6 by 6 Jacobian, right? Where worst case is you have a 6 degree of freedom joint. So this does not scale with NQ, right? This happens in constant time, independent on how large your system is. And that's what we're going to do, right? And then I think we just now try to solve for FBB. And I do the same game of plugging in and replacing is, okay, and I'll take this equation. I have to replace the blue quantity. Where does the blue quantity come from? From here. But there's the brown quantity that I don't know well. I can get the brown quantity from here. And then I just substitute my Q double dot. So FBB from the first equation is given as that. green FBB, FBB constrain, this blue quantity. I get this from the second equation, which I write down here. And you see there's a bit of a coordinate transformation happening with this ABC hat, because this is stuff expressed for the center of gravity of body B. This is stuff expressed for the center of gravity of body C in the respective coordinate systems. So there is this transformation matrix. But other than that, I just plug this in. Then I have ACC as my unknown. I take this entire expression, which I get from my motion across the joint. And then I have Q double dot as my unknown. And that Q double dot I can then insert here. And I can compute FBB. And again, nothing here scales with n, because these are all 6 by 6 matrices, 6 vectors. These are all spatial quantities that somehow describe the motion of body B, or articulated inertias, which are either 6 by 6 matrices or bias forces, which are 6 vectors. And then I can do a bit of rearranging here, where sort of the key thing is that I have these quantities ABB, the acceleration of my handle. And I see in front of that, I have a 6 by 6 matrix. In front of that, I have a forward transformation, 6 by 6 matrix, backward transformation. But together, this is also a 6 by 6 matrix. So in front of ABB, I have two 6 by 6 matrices that I can just add up to a 6 by 6 matrix. And I will call that MA. And here's how MA is being computed, right? It's a little bit more involved. Because, oh, sorry, I overlooked this one. There's a third quantity, but sort of same story, right? Forward transformation, matrix, backward transformation, Jacobian, matrix, and so on. I missed the Jacobian. Forward Jacobian, backward. Anyway, here's the full term, right? The important thing is this is 6 by 6 matrix. And then everything else depends either on velocities or on this tau, sometimes implicitly, right? Because I have these bias forces which depend on velocities, and taus, I have these bias acceleration which depend on velocities. But all of this I can put together into a bias force, right? And just rearranging, and I can then rewrite this as ma times acceleration, spatial acceleration of body B is some bias force plus the force that is acting on the handle. And that is now proof that my bold claim here is actually true. I can show you that it's true for two rigid bodies. I can show you that it is true if I connect two rigid bodies and select one as a handle. I can compute the articulated inertia, the bias force of that new handle, using these equations, right? That's my new bias, my new articulated inertia. That's my new bias force. To compute these, I'm manipulating 6 by 6 matrices. There's some Jacobians involved, but roughly speaking, right, this is somewhere between 1 and 6 dimensional. So it doesn't scale with the number of degrees of freedom. This process of combining two articulated inertias to form a new, larger rigid body with one articulated inertia happens in constant time. Okay? How do we use that? And to that end, I want to dive a little bit now into the details. And some of this is repeating what we did before, or what we didn't do before, right? I just showed you this very quickly on the slides. And I want to focus on a joint that sits between a body that I will call I-1. Here's my joint. And here's my body I. And I will call the joint also index I. So joint I is the predecessor of body I. And that joint has a known Q, a known Q dot, and a known tau. And all of these, let me space this out a little bit. All of these are just the quantities of the joint. So this is why I call this Qi, Qi dot, and tau I dot. Right? Written here as vectors because they can be multidimensional, but for a rotational joint, these would just be scalar quantities. The thing that I want to know is the acceleration across that joint. I also assume that I know, what am I doing? A, B, I-1. I also assume that I know the acceleration of the predecessor, spatial acceleration, so translational and rotational. How can I make that assumption? Right? If you don't believe me, then I say body I-1 is root, and we see from there. But for at least one body, I can say I know it. Right? For root, I know it. If I do forward dynamics, these quantities are given. So this is really my unknown. This body BI has an unknown acceleration, which I will call ABI. And that one is unknown. That gets a question mark. I don't know how that is moving because obviously that depends on Q double dot I, and I don't know that yet. And that body is actually not a leaf, but it is connected to more stuff. Right? So it is a handle in the sense of an articulated body. It's a handle of this entire subsystem that sits behind. And what I also assume is that I know the articulated inertia and the bias forces of that body. And all of that is given in BI coordinates. Okay, so this is my assumption. We know the articulated inertia. We know the bias force. We know the joint torques tau I. And we know the acceleration of the predecessor, ABI-1. There's one thing that we don't know, because there's a joint, and at that joint we have some constraint forces that I want to express here as if they are acting on the center of mass. And here's the corresponding reaction force, which is minus F C. And I express this here again as if it is acting on the center of mass now of body I minus 1. Right? That is another big unknown in this process. But we can now compute our acceleration of our successor. We can at least write down our acceleration of our successor, which is going to be this transformation matrix AB I minus 1 BI transpose. So the transformation from I minus 1 to I coordinates multiplied with the spatial acceleration of body I minus 1 in I minus 1 coordinates, plus stuff that happens at the joint, which I will write with this joint Jacobian j hat I, which will give me, again, quantities in BI coordinates. And that gets multiplied with QI double dot. So just the accelerations within this joint. And then we have a bunch of bias terms. Which we can compute, but you saw before, right? That's half a page of equations to compute them. So that we know. We also know that there is an inherent relationship between the torques, the motor torques at that particular joint, and the overall 6-dimensional constraint forces, which uses the same Jacobian just in its transposed and gets multiplied with this vector of constraint forces given in BI coordinates. So I'm basically just restating things. And since we have this articulated inertia, we know that there is a linear relationship between the accelerations of this body BI and the forces that are acting on body BI. And in this case, the forces are the constraint forces, right? What we wrote as FC in BI coordinates. So the blue stuff, right? And there's also, of course, the bias forces P hat, also in BI coordinates. So tau I is going to be, well, this here. So it's going to be ji hat transposed in BI coordinates times this constraint force, which I will get from this equation here. So the same thing I just rushed over, I'm doing here again a little bit slower, just that you see it at least once in detail. So this is acceleration of my body times articulated inertia, and now minus my bias force. Also in BI coordinates. Is equal to, and now the only thing is I'm left with doing is to replace that acceleration with the expression that we have up here. So make it a function of q double dot. So we get j hat I transposed in BI coordinates times our articulated inertia, mi, which now gets multiplied with AB I minus 1 BI transpose. That should get a hat, because these are spatial transformation matrices. The acceleration of my predecessor, plus the Jacobian of that joint times the acceleration of that joint plus my bias forces sigma I hat. Again, a spatial quantity. So this now covers my BI, and then I have here minus the bias forces of the articulated inertia. So of articulated inertia I in BI coordinates. And now I can rearrange, get the stuff I'm trying to solve for to the left-hand side. And that stuff I'm going to solve for is having this form Ji transposed times articulated inertia of articulated body I times Ji times Q double dot equals tau I minus all the rest, right? And all the rest is going to be Ji hat transposed Bi times, what is all the rest? We have the articulated inertia times the acceleration of the predecessor with the appropriate transformation matrix. We have taken care of the Jacobian times Q double dot, but we have to think about the bias accelerations. And then we have the bias forces. And this is the same thing in a sense that I stated on the previous page, where I now have my equations of motion written in the space of joint I. The equations of motions in joint space of my joint I. Right, so you see, if I have that articulated inertia of the remaining subtree and the acceleration of the predecessor, I can do this, right? I can project everything into the joint space, and that projection happens in constant time because none of the involved quantities is larger than 6 by 6. And that projection can then be solved for accelerations in constant time because it requires the inversion of a 6 by 6 matrix. So I can solve this for Q double dot, or Q double dot I. And when I have that, when I know what Q double dot I is, then I can go back to this equation here and compute the acceleration of the successor, right? So solve for Qi dot, double dot, and then compute the acceleration of body Bi. And then I'm prepared for the next joint, because then I know the acceleration of body Bi, and I can then go ahead and solve the motion for joint I plus 1. And all of this happens in linear time. So what is the complete algorithm? The first thing is you do an outward pass, and you compute everything you can compute, right? And we're doing forward dynamics, so I can compute my positions, I can compute my velocities, I can compute my Jacobians, and I can compute my bias stuff. We've seen in the Euler recursive Newton-Euler algorithm that that outward pass is order n. You start with the position of root being 0, so that's the starting point of my interaction. I should write this here as spatial quantity, even though we haven't defined this for positions. But you know what root is doing. You do this joint by joint in an outward pass. At every joint, you have to compute the relative motion across the joint, which is at maximum a 6 by 6 operation. Doesn't scale with NQ. If you do this for all bodies, of course, you have to do this once per joint. And once per joint means that the overall complexity of this first outward pass is order n. It's the same first outward pass that we had in the recursive Newton-Euler algorithm. Then comes an inward pass. So now we go from the leaves to the root. And what do we compute as we go from the leaves to the roots? These guys, articulated inertia and bias forces for each possible subtree that we can ever encounter. How does that work? Well, you start at a leaf. How do I compute the articulated inertia and bias force of a leaf? This one, right? I can do that. Can be done. I can do this for this guy. And I will also do this for this guy, even though it's not a leaf, but you would believe me that I can compute sort of the individual term just for this particular body. And then I start combining stuff. So I could, for example, combine this leaf with this body to get the new articulated inertia of basically this subtree with this body as its handle. And if I have done that, I can now compute the articulated inertia of the entire subtree with this body as its handle. And this is what I would call BI, or in this case, BI plus 1. Right? And then you see where this is going, because if I know the articulated inertia of BI plus 1, I can do one last combination where I combine this with this to get the complete articulated inertia now of body BI. And so I start from the leaf. For each body that I visit, I first compute its independent articulated inertia and then combine that articulated inertia with the articulated inertia of its children. And I can do this in a recursive fashion moving inwards. Right? I always need to have the articulated inertia of the children that are connected to a particular body. But once I have that, then I can combine things one by one. That's my inward pass, and I have to do this to compute these articulated inertia quantities. What's the computational complexity of that? You have to go through the whole tree, and then you have to think about how often do you have to do certain things. For each individual body, you have to do this, NQ times, but these are 6 by 6 matrices, so it scales with order n. And then for each joint, I have to go through this, right? Because each joint means I'm combining two articulated inertia, which are all 6x6 quantities, and I have to do this for NQ joints. So I will have here also a computational complexity of order n. So overall, this is an order n process, right? For each joint, I do the same thing, very involved, but not dependent on what the other joints are doing. So this is my second step, my inward pass, where I compute these articulated inertias and bias forces. And it's basically based on this idea that for relief, I know what my mass matrix, my articulated inertia is, right? This is, someone said it before, right? For relief, we know this, recursive Newton-Euler equations. For relief, we know this, rigid body dynamics, Newton-Euler equations for a rigid body. And then I have everything to do what I just described, which is a last outward pass. And along that outward pass, I now compute all my accelerations q double dot I. And I can compute all my accelerations bi. And I can do that because I know that the acceleration of root is going to be 0, right? This is this idea that I just sketched out. You say, I don't know, I know the acceleration of root. I know the articulated inertia of the thing that is attached to root through joint I. I know the joint torques at joint tau I. And I can use these equations to first compute qi double dot. And once I know qi double dot, I can compute the acceleration of the successor. And then I would look at this joint. I would take the articulated inertia that is sketched here in brown, do the same computation, get the acceleration of this guy, look at this joint, look at the articulated inertia of this body, which is just a single body, do the calculation, continue here. So it's an outward pass, and it's also order n, because in every step in the process, I go there joint by joint, and for each joint, I have to solve this equation, which is at max 6 by 6, and then I have to solve this equation, which is at max 6 by 6. So it's independent on how many other joints there are. So for each joint, I have something constant in time. Overall, this algorithm is order n squared. It's order n. What am I saying? Don't you hate it, right? If you build up to this punchline and then you screw it up. Horrible. Horrible instructor that you have. Sorry. Still blows my mind. Right? Everything we learn, the equations that we derive, the equations that look pretty, they are all order n cube. And there comes someone, Roy Featherstone, by the way, that's the someone, who figures out if you do this joint by joint, if you do it in a smart way, if you think about these quantities, these projection methods, these mass matrices in a bit of a broader way, you can do this in order n time. And I think there's interesting information in there, right? If you ever have to tune a PD controller for this joint, right? There's often this question, what's the mass? Right? If I have a PD controller, I want to set a certain frequency, but then your mass is somehow important. Well, there it is, right? That's your mass, right? And it's configuration dependent, which makes stuff a little bit more involved. But if you think about this, you can, in your controller, you can compute this guy, right? And then have adaptive gains that sort of make sure that your joint controller optimally reacts with some, phase reserve, all the quantities that you want to be as quick as possible without getting unstable. And this will tell you what the mass is that is involved. Right? For a rotational joint, that's a scalar quantity that depends Yeah, here this depends only on Q. So if you know all your joint angles of the rest, you know how heavy this thing is. Right? It also allows you to reason about questions of design. How large should that motor be? Right? What's the worst configuration? Sometimes it's obvious, right? If I have an arm like this, that's going to be my maximal inertia at this joint, right? If I have this configuration, if I move my stuff in, right, I will have a much smaller acceleration. But may not be that obvious if you have other things happening in terms of, these are unconstrained joints or loosely moving joints. So what's the inertia if I do this, right, without keeping my arm fully extended? That's it. No more paper. Class is done. Any questions about articulated inertia? Then let me do a summary, and this is now a bit of an open question for me. Has Iskander, who has been working on these slides during the last hour, did he finish? We'll see. We'll find out. You're so quiet today. Did I overwhelm you? Here's my class summary. What have we learned? And if I had to say this in few words, I think the most important thing that you should have learned is it's physics. And it's something that I keep stressing and I find very important. This is why you get here a bunch of animations on this. It's physics. What does it mean? Every quantity that you get has a unit, and it makes sense to reason about this unit, right? Is it a force? Is it a torque? Is it a mass? Everything, right? Every number that we wrote down, every symbol has a unit, and that unit gives it some physical meaning. They're real. I sometimes read about constrained equations of motion, and they introduce lambda as a Lagrange multiplier. And you can do that, right? Mathematically, it's equivalent. That's the reason why these contact forces, what we call the contact force, are called lambda, because the nature of a Lagrange multiplier, and then some people get totally excited, which I can kind of understand, that there's these parallels and that you're basically doing a constrained optimization, and they call it lambda, and they say it's just there to make sure that the equations works. Right? It's a constraint in a constrained optimization, and there's your Lagrange multiplier. It's not a freaking Lagrange multiplier, right? It is a force. And if you build a robot, there's going to be some bearing that has to withstand that lambda. And if that bearing doesn't have the right size, that lambda is going to literally fly into your face, right? So it's not a random Lagrange multiplier. These quantities, right, this m articulated, it's a very abstract quantity at first. But if you grab your robot and you shake it, that's what you will feel, right? If you project stuff down into a joint, that's what your motor feels. And knowing these quantities, right, enables you to tune controllers in a better way, to be clever when you do planning, because in certain configurations, think boxing, you want the MA or the M lambda to be large. In other configurations, you want them to be as small as possible because you want to do very delicate maneuvers, right? And that's something that you can see and feel. The vector spaces, right, they're also real. You can put sensors in there. You can measure this. And I have a philosophy for this class that I say this, knowing this and having this physical intuition is useful because it allows you to do things in a more creative fashion, right? And I think that's something that sets this class apart. I think the more abstract approach also has value, right? To think about math and to work with equations and follow a more formal method. But in robotics, it's often in the end it has to work. And then if you have some intuition, that helps, right? And we saw some ideas of how what we saw here in the context of a dynamics class can be employed in other applications. So if you think about our virtual model control, right? That was, right. You see that I don't use PowerPoint a lot, right? If you think about virtual model control, right? That's just about projecting forces, Jacobians used for control. We could think about virtual constraints. We didn't do this in this class, but imagine if you say, I want my robot to basically move to a certain point, and then don't go any further, and basically move in this plane. You could write a simulation now. Actually, you are writing a simulation now where you say, what are the equations of motion? What are the forces that are acting here? What are the resulting angular accelerations, and so on? But you could turn this into a controller and say, well, hold on. If there's a force lambda, could I just project that force lambda into my equation of motion and send those torques to my motors? And my robot will behave as if there's a wall. And you can use that for some control purpose, right? To make sure your robot can move in free space but cannot go through the wall. Right? Whenever it goes to the wall, you compute the torques. Right? It's not a simulation, it's a controller. This whole idea of working in operational space, I share a paper later on, right, is basically based on this, that you want to think about working in different spaces when you have a robot. And the most natural is joint space, because that's where your motors and your sensors are. But if you think about your robot doing something useful, right, often it makes more sense to think about the end effector space. And now, what is the inertia, the masses of the end effector space? But end effector space doesn't have to be 6D Cartesian space. It could also be some weird operational space where your robot has two hands, but they can only translate, and then you get a weird 6-dimensional space, and you may get collisions within this. And no one has ever done this, but you have the tools to think about it now in a different way. Oh, right, there's my operational space. There's a weird mass associated with it, which basically just means if I move in this operational space around this axis, that's the mass that I'm going to feel, and so on. Right? And that becomes then importantly when you start thinking about tuning gains, getting certain responses. Right? As a control engineer, you always want to know what's your mass. And here the mass depends on, well, what's the space you're working on, right? Is it joint space? Is it constraint space? Is it operational space, Cartesian space, and so on? What have we learned? This is a bold claim. Not a lot new stuff, right? It's basically just this. F is m times a plus some lever arms, right? Jacobian, done. I hope that on some level you appreciate this, right? You get the slides. It's, of course, hard to do right? And the complexity, I think, of this class is not in the complexity of the physics, but in the issues that you have high-dimensional motion, right? You have 3D kinematics, which means rotations are a nightmare. Everything depends on everything else, and intuition is lost very, very quickly, right? So I have this focus on intuition. Now comes the warning, right? For any reasonable system, your intuition will very quickly fail you and won't help. Sometimes you can probe with simple examples, right? We talked about this. What happens if I set my velocity to 0, my acceleration to 0, gravity to 0? Do these other terms make sense? Does the resulting motion make sense if I go into certain configuration where my nonlinearities, my trigonometric functions are 0 or 1? Does at least that correspond to my expectation, right? If a mass matrix of this robot is very difficult, but in this configuration, it may actually be very simple, and you could reason about, okay, if I push here, what should be the mass that I feel? If I push here, what should be the mass that I feel? What are the coupling terms? And that helps a lot. The other thing that was a nightmare to you guys, I don't know, my experience from past classes, you may be different, moving coordinate systems and differentiation. Right? This difference between I have a velocity which can be expressed in different coordinate systems. I have a physical velocity, I have a relative velocity. How are they all connected? And there's all these choices that you have to do. What are the best generalized coordinates? How do you pick your coordinates for your constraint space, your motion space, your end effector space? How do you implement this, right? And I didn't answer all the questions in this class, but I hope I made you think a little bit. When you ever get in this situation, do I do my equations analytically and then let the code optimization take over? Do I do the recursive implementation, which is quicker but maybe a little bit more error prone? Do I do the canonical form of the equations of motion, which are easiest to interpret but maybe not as performant? Again, depends on your programming language. In MATLAB, they're probably the best thing you can do, because for loops are slow and matrix multiplications are quick. But all of that needs also a lot of experience, even if you use off-the-shelf software. And maybe that's also something that this class enables you to do the next time you pull out your SimScape multibody or whatever software package you use, and you're tasked with these equations, and then you get an error. You have a bit of an understanding what's going on. Is it a kinematic singularity? Is it somewhere a mass that I didn't assign right? And I hope that helps then with using other software as well. In terms of content, we started with a little bit of programming stuff. So we got to know SimScape multibody dynamics. We learned object-oriented programming recursion. This is a lot by design. Part of the reason why I made this class the way it is, because talking to prospective students, I always had this conversation which started, do you have programming experience? And everyone said, yeah, I know C and Java and MATLAB. Have you done any projects? Yeah, we've done tons of projects in Engineering 101 and Einführung in die, how's it called, PSE, Programmierung und Softwareentwicklung. And you stand there and you have no idea how to program. Because the only way to learn how to program is if you do one big project start to finish. That's when you learn about how to structure your ideas, structure your strategies, put your code into, this is what we did here, right? Put it into different objects, start thinking about recursion, thinking about inheritance, large scale, not just hello world, right? But something that has a complexity that I would say none in this room, including myself, can grasp at once, right? So you learn about how important documentation is, how important it is to specify variables in a clean way, to structure things that it's not all spaghetti code, but that functionality is probably in the kinematics part, and that functionality is in the dynamics part if I have to look it up. So I find that something very, very important. We learned about basics, vectors, coordinates, rigid body dynamics and kinematics, which I actually considered a repetition, but I think it's also very useful to see this multiple times from different angles. We talked about constraints and kinematics in a very general way, and then we did these projection methods to get our equations of motion and rounded it off with implicit constraints and collisions. This is where we started projecting stuff from one coordinate system into another, and then I consider this more as fun topics, these ideas of virtual model control and algorithmic complexity, which don't follow sort of how do you say the structure or the stream that we have here, including what we saw in the exercises. Congratulations, you just built your own multi-body dynamics engine. Not from scratch, using a lot of templates, but I think you all did the key parts, and through the projects, I hope you're also at a point where you now understand how to extend it, to add your own joints, to use it for different projects. And it can do collisions too, which some off-the-shelf frameworks cannot do, and they cost you a couple of €1,000 a year. So the framework that you created, has a market value. I wouldn't say of a couple of thousand euros a year, but this is not, it's not something trivial. It's not hell of world. I haven't tried it, but I'm pretty sure when you ask ChatGPT, can you do this for me? It's not going to work. And I think that's quite an achievement for a class to create something of that complexity, to fully understand it, start to finish, every little bit. It has crappy graphics, that's my fault. But the inner workings are quite intricate and can do more than, some other software can do. There's, again, this intuition part. The graphics are crappy, but I like visualizing things. And if you ever gonna build your own model of some computational dynamical system, the first thing you should do, the first thing anyone ever should do who tries to model a multi-body dynamic system is make an animation. As a human, I can look at this and can immediately tell you if something is wrong, is fishy. That's moving too slow, right? It looks like that mass is too large. Wait, that joint should move this way, but it's moving that way. Try to figure that out from a bunch of plots. No chance, right? If accelerations are correct. If I look at this, that looks physically reasonable. There's no proof, but allows you to catch, the easy mistakes, the masses that are set to 0, the sign errors, the joint axes that are not oriented well, right? And the arrows should also try to give you a bit of an intuitive understanding of what is an angular momentum, what is an angular acceleration. Especially in 3D, that's not always super intuitive. This idea, right, if I have something that's rotating, and then I'm rotating it, you think that's the angular acceleration. But since my angular velocity is about this axis, the main effect is not creating a rotation about this axis. The main effect is about changing the axis of the existing rotation. So my angular acceleration points in a completely different direction. And looking at this can help build up that intuition and help you debug your future projects. There's a little bit of future reading. These collisions, Pfeiffer and Glocker, this is the closest in terms of notation that is to our course. If you want to read a bit more on the background. We didn't talk about flexible links. This is a rigid body dynamics class. So if you want to move into books that talk a little bit, not only, but include flexible links, these are two good choices. This is Roy Featherstone's book. It's a tough read because he does not only introduce his rigid body dynamic algorithm, but he also uses different coordinates and different ways of representing multi-body motion. So, we say motion of the center of mass plus rotation. He says, how does that body move through the origin of my center of mass? Right? And so there has a rotation, and you're basically sitting in the center of mass, and you're looking, not center of mass, the origin of your coordinate system. You're sitting at that origin of the coordinate system and see all these bodies, which of course have infinite dimension in this idea, are moving past that origin, and of course that describes rigid body motion. And then he introduces some operators, and it's a bit of a hard read. That's why I try to stay away from this. There's this idea of screw theory, so having joint vectors, 6-dimensional vectors, that's also used in this Murray-Lee Sastry book. And then there is this paper I showed you about ambiguous collision outcomes, and then there's a bunch of papers on control. Virtual model control, this is about operational space, these ideas of using virtual constraints and projections to get more complex control. And this is virtual model control, in which there's null space projection for redundant or controlled robots. All papers going sort of in the same direction. If you're curious, how can I apply this in a controls background? Okay, what's next? This is now my pitch for stuff. We have a specialization area. If you are uncertain, if you're interested in robotics that look like this, we're maybe not the first choice. We're interested in the next generation of robotic systems. And I think you saw this in this class, where we reason about different spaces, not only joint space, where we reason about contact, where we reason about, in other classes, not in my class, about flexible structures, and so on. And so this is where I want to pitch our specialization area, which tries to teach you about the new robots, the robots that will be around in 10 years. Here's our list of courses. This is more for your information. We just went through computational dynamics for robotics. I will be teaching another core course this coming summer, which is called Dynamics and Control of Legged Locomotion, which deals with the dynamics of legged systems. There's a lot of overlap with what we do here, right, in terms of multi-body dynamics, collisions. But there's also some interesting concepts where you look at this and say, this is a periodic motion. This is basically a limit cycle. How can we assess stability? How can we find periodic motions? And so on. And then, of course, there's this question of how do I control stuff? If you are taking our specialization area, and if you are a mechanical engineering or mechatronics students, you will not be able to take this class. This has to do with the structure that you need one core class, one 6LP class, and you need a 3LP intern practical course. But you can get the same content by basically taking the first half of this class, which is a class that's called Dynamics of Legged Locomotion, which runs for half a term. And then we have a dedicated practicum, so practical component, where you get to implement the controllers. So it's very similar in terms of content, a little bit more hands-on because it has this lab course component. And then my colleague Philip Rodemund teaches 2 courses on soft robotics. One is called Fundamentals of Soft Robotics, so this will start in the summer term. Robots that are not made out of metal, rigid parts, sort of the antithesis to this class, but robots that are made from deformable things, rubber, silicon, driven by pneumatic actuators, by electrostatic actuators. So sort of a little bit futuristic, but we slowly see these ideas also creeping into applications. And then in the winter term, there's a more applied course which has a lab component and talks about the design. If you like the topics, we offer tons of student projects. Go to this page to see what we currently offer. The more important thing is we just installed a mailing list, and I encourage all of you to sign up to this mailing list. It's very low traffic, so you're not going to get spammed. But whenever we have a new master project, we send it there first. Whenever we have a HEVI position, we send it there first. Whenever we have a PhD position, a job, we send it there first. And it's totally monitored. So it's things not only from our institute, but also stuff from the area, Max Planck Institute, for example. Sometimes we post something there. It's super useful, and it's not annoying to be to subscribe to this list. We have a second list, which are our weekly seminars. There you get an email a week. Sometimes people are just curious what we're doing. Sometimes there's some interesting talks that you may want to join. There's no commitment with signing up to this mailing list. It's just you're up to date. And if once a year there's something that you find interesting, you can just come and join our seminars. Here are a bunch of sample projects. I go through them quickly. I just want to give you a feel of what is currently offered. There's a lot of optimal control stuff where we're trying to optimize legged robotic systems, but also some simpler prototypes, asking questions of how to drive them in an energy efficient fashion, reasoning now more about control topics, trying to go ahead and convexify problems. So a good mix between numeric simulation and theory. This is cool. I've talked about the passive dynamic walker in this class. Here's a version from a colleague in Japan who builds this machine that just walks by itself. without any motors, without anything, sitting on a treadmill. And in this project, we would like to build one of these, right? And that is first and foremost a question of modeling and simulation and design optimization. And this is what we have. So what you see here, it's an animation based on the methods taught in this class of a system that has no motors. None of these joints are actuated. Here you see our virtual 3 degree of freedom joint, which in this case actually is going to be a physical 3 degree of freedom joint. Gravity is pointing a little bit to the right to drive this. And this is walking completely passively, right? So we're trying to build this. So getting a, where's our presentation? Getting a CAD model, working with the machine shop to build it, and then basically having an iteration where you have to design, optimize the design, but then as you build it, you learn more about the constraints, right? You say, oh, I'll make this mass distribution, and the workshop tells you, yeah, not feasible, right? I cannot make this out of thin air. Just as an example of a more applied build-a-robot project. This one, there's a bit of a trigger warning. We have here a so-called kangaroo rat, and hidden here in the bushes is a rattlesnake. This was taken in the California desert. The kangaroo rat will survive this incident, but I have to show you this video twice, and if you don't want to see the attack, close your eyes. So this was, showed you this once. And the experience is that everyone stares at the open mouth of the snake. Now I show you this again. I will rerun this. And now I ask you to look at the kangaroo rat through the entire interaction. Keep your eyes fixated on the kangaroo rat and see how it jumps, how it uses its tail to reorient itself in space. First around the roll axis, and then it's doing these whiplash motions to orient around the, what is this? Sorry, pitch roll, yaw axis to get away from the snake. And this is something that we want to investigate. How does that work? So it's, from an engineering perspective, an optimization and optimal control problem. From a biology perspective, it's about functional morphology. And so we have a collaboration with a biologist. And then here's a bunch of projects that are focused more on soft robotic systems. You will find all of this on our webpage. I just want to give you a bit of a flavor of what we offer. This is a subscribe and like part of the video, right? And then, as you do in a good YouTube video, right, there's the teaser, then the main content, then comes the paid by, and then in the end comes the bit that you came to watch. And this is the exam. Logistics, it's a 30-minute oral exam. You get 6 pages of handwritten notes, 3 sheets, 6 pages, A4. Can be written on a tablet and printed out. We don't care about this. We always recommend write it by hand. We will bring your project report to sign it, but also if you want to show us something in your project report, please go ahead. I will upload those slides, so no need to take pictures. Students often ask themselves, can I use a cheat sheet in an exam? The answer is yes, of course. The way you should use it is not to frenetically look for an equation and then copy that equation to the piece of paper that's lying in front of you, but just say, hey, you asked me this, here it is. Right? You asked me that, you'll find it here. You asked me this is on page 2 of my report. Right? For us, this is not so much to check whether you have known stuff by heart, but did you know where to find it, and that you know what the concept is that we're talking about. So it's basically not copy, but pull out your cheat sheet and say, here's the equation. Right? You don't have to read it to me, you just have to show me that you know where to find it. Location is at the Max Planck Institute. This is my office. We have detailed instructions in your email. There's a nice waiting area with couches and tables outside on the staircase, so you can just sit there, prepare yourself for the exam, and then we'll call you in. Make sure to take some extra time to find your way there, especially if you've never been to MPI. It's in Busenau. It's a 20-minute walk, 10-minute bus ride, but the buses don't run very regularly, so make sure to be there on time. They also have a very good canteen for after your exam. Highly recommend eating there. It's open for everyone. You should all have received an email with your logistic information. If you have not, if you have any doubts about that, let us know, right? As soon as possible, and we'll fix it. Content, well, everything in class and exercises. It's an oral exam, so that tells you we focus more on concepts. We have the project. We will work along the project. So, be prepared to explain how your project works, especially the things that you did yourself. How did you find your joint spaces? How did you implement your constraints? Can you show us your controller? And then we dig into stuff and say, okay, I see you here in your code, you call this function, even though you didn't write it, what is it doing? Right, and be prepared to answer this. If you've done the exercises, if you've done the project yourself, you should know all this by now. But just prepare yourself to explain these things. And along the way, we will then dive into the theory, right? Oh yeah, that piece of code. Can you, explain to us where that comes from? And this is where you pull out your cheat sheet and say, yeah, it's that equation. And that's where I will not stop, but will ask, okay, what are these terms? Can you derive them? What is the connection? Where else does that show up? Right? So we will have a very active discussion on often on your cheat sheet, your report, and your code. It says here, compute partial equations of motion. Sometimes is a part of the exam. It's easy to write in, sigma equals j dot times q dot. And then a lot of people surprisingly fail when you ask, can you do this for a system with 2 degrees of freedom, right? Because all of a sudden, okay, what is q? What is x? What is j, right? So we want to see that you not only can write down the basic equations, but that you can apply them, that you know what they mean in a content, in the context of an actual problem. How do you prepare? Talk to each other, work with each other. On Thursday, we don't have a class since I finished everything almost on time today, but we will meet in the room. We can use this as if it was a regular exercise. So bring your computers, we bring extension cords, go there, work on your projects, talk to your peers, ask us questions. We will be there as we would be on a exercise Thursday. Learning groups, the best way of really understanding stuff is by explaining it to someone else. Right? So in this interaction of someone who didn't understand it and someone who understands it, you always think that person profits, but it's the person who explains who profits most. So work in a group, explain stuff to each other. If you have any questions, we have the regular office hours until the project is due. So Monday and Thursday. And afterwards, we will do office hours only by appointment. So you email Iskander, give us a few days to arrange meetings. We will group people so that we don't do 25 individual meetings, but maybe 5 meetings with 5 people, which also helps you because there's nothing better than someone else asking questions that you haven't yet thought about. So that's also very useful. I will not answer email questions by email. If you write me an email, you get as a response, please post to the forum. And we answer there because, again, right, others will profit from the questions that you ask. And sometimes it's something I wasn't quite clear about in the lecture. At this point, I want to stop. I know it's a little bit past 1, but do you have any questions? Yes?
So said we will get our project. Is this including code or only the notes?
You have a screen in front of you with your project, right? And we tested it. And if it fails, we will ask you where did it fail. And if it works beautifully, we will ask you, can you walk us through this? What's happening here? And of course, we will focus on the things. And it serves 2 purposes. One is we want to check if it's your own work. Right? I mean, you can work on this with others, but your submission should be your own submission, and you should really understand what you submitted. Right? This is nothing to be afraid of. But if someone just asked ChatGPT to write their code for them, or copied the solution from someone else, we would very easily check that. So you have the screen in front of you, you have the printout next to you, you have your 6 sheets of your notes, and then you have some paper to write on, and that pretty much covers my entire desk. Yeah. Good. Any other questions? Concerns? Yes, concern.
3 sheets of A4 paper. Could we potentially just have
Single, that's fine too. Yeah. It's always, if you say 6 pages, then people come pages front and back. So 6 pages front or 3 pages front and back. A4. We also accept letter, but no other formats. Any other questions? Then, here's my last slide. There's a little bit of this ahead of you in the term break, but I also hope there's a little bit of this. Relax, recharge. Good luck with everything. I hope to see you around, not only in the exam, but afterwards. You were an interactive, fun class. It was a lot of fun to teach this term. Felt good. Thank you.